So, we are at the end of the course, we have 2 more sessions. We will talk about absolutely continuous functions. So, recall that we defined absolutely continuous measures. So, I will explain the relation between absolutely continuous functions and absolutely continuous measures. So, this is a very classical result. Essentially, when the fundamental theorem of calculus which you have learnt in your BSc is true. So, if you recall that, you will see that if I have a continuous function and I integrate it, I will get a differentiable function, and when I differentiate that function, I will get back my original continuous function. Okay. And the integrals involved are Riemann integrals, right. So, we will change that to Lebesgue integral, and we will see that absolutely continuous functions. So, that is a property which we will define today. That property is what tells us when the fundamental theorem of calculus is true in this general setting. Okay. So, let us start with that. Okay. So, definition. So, we will start with a definition of absolutely continuous functions, and then we will relate it to the measures. So, let us take a function f from a b to the complex plane. Okay. So, this function is said to be absolutely continuous. So, sometimes I will write just AC just to say absolutely continuous. If okay. So, this is very close to how we define continuity, but it is a much stronger property. Okay. So, if for every epsilon positive there exists a delta positive, of course, delta will depend on epsilon such that summation I equal to 1 to n. So, I will tell you what n is, modulus of f of beta I minus f of alpha I. So, I will tell you what alpha I and beta I are. This quantity should be smaller, less than epsilon, for any n. So, that is the first thing. So, n is the number of intervals we will be looking at, and that is also important, any disjoint collection of intervals, of segments or intervals alpha I beta I. Okay. So, I equal to 1 2 etc. n. So, we have n intervals and they are disjoint collection, okay, of intervals alpha I beta I such that their lengths add up to delta. So, summation I equal to 1 to n, the length of alpha I beta I is beta I minus alpha I, and that should be less than delta. Okay. So, let's try to understand this a little bit more. So, if I look at a function defined on AB, so let us say this is my interval AB. Okay. I have these intervals alpha 1. So, I have alpha 1 beta 1, right, alpha 2 beta 2 etc. n of them alpha n beta n. Okay. Remember, I can take any n. So, any number of intervals, the condition is that it should add up to less than delta. So, for every epsilon I should be able to get a delta, so that whenever this is true I have this quantity to be less than epsilon, right, that is the definition. So, alpha 1 beta 1, so this is one interval, okay, alpha 2 beta 2 another interval, maybe alpha 3 beta 3 is here, okay, some other interval, they have to be disjoint. The point is that when you add the length of all these, right, that should be less than delta. If that happens, then I should have this inequality, right. So, for every epsilon there should be a delta, so that whenever this happens I have this inequality. Okay. So, what is the relationship between, so recall that this immediately of course says f is continuous. So, if I take just one interval, take just one interval, that is n equal to 1, you will get f is continuous. So, continuity is a very weaker property compared to absolutely continuous functions, continuous property. We will see that. So, if I take one interval, then I will have a delta such that, so instead of this mod x minus y less than delta will come, right, instead of this, and I will have mod of f of x minus y is less than epsilon. So, that is simply continuity. Okay, so let us see what has it got to do with measures. So, let us take a very simple example. So, I take capital F, okay. Well, maybe I start with G continuous, let us say, from AB to C continuous, and let me also assume that g of x is positive, okay. That is not necessary for anything we are saying, but this is to just make things easier. And define capital F of x. So, this is essentially the fundamental theorem of calculus, or part of it which you have seen several times, g of t dt, right. Then as an aside, we know that f is differentiable, and f prime at t equal to g of t for every t in AB, right. We know this. But g is positive, so we can define a measure. So, define a measure using g. Let us say nu of a equal to integral over a g dm, right. M is the Lebesgue measure on, of course, Lebesgue measure on the interval a. Right. This makes sense. We know that this is a measure, right. It is a countably additive positive finite measure because it is continuous, and so g is bounded by a constant, right. G is in L infinity, and so nu will be a, so this implies nu is a bounded measure. It is a finite positive measure, okay, finite positive measure. But then we know whenever we have such a situation, for every epsilon positive there exists a delta positive such that the measure of a is less than delta implies new measure of a is less than epsilon, right. That was because it is absolutely continuous, right. Nu is absolutely continuous with respect to the Lebesgue measure. So, we know that this is true. Now, let us try to interpret this in the terms we started with in the definition of absolutely continuous functions. So, when I say, so if I fix an epsilon, so for epsilon positive there exists a delta, right, which does something. So, for that we choose, so let us say this is AB, and let us choose intervals alpha 1 beta 1, okay, alpha 2 beta 2, alpha, let us say n beta n intervals, okay. So, they are disjoint. So, write A as union alpha I beta I, okay, I equal to 1 to n, disjoint sets, such that summation beta I minus alpha I equal to 1 to n is less than delta. Okay. But what is this? This is the measure of A, right, because it is a disjoint union of intervals, so measures add up. So, if this happens, if measure of A is less than delta, then I know that nu of A is less than epsilon, right. That is the absolute continuity of the measures. But what is nu of A? So, nu of A is integral over A of g dm, right. So, well, this is g is continuous and so on. So, this is the usual Riemann integral gt dt. But what is A? A is a disjoint union of intervals. So, this is summation I equal to 1 to n integral alpha I to beta I gt dt, correct. So, this is fine, okay. But G, so we remember we defined a capital F which did not do anything so far. So, capital F is the integral of G. So, what is this quantity by a fundamental theorem of either one part of the fundamental theorem of calculus? This is summation I equal to 1 to n f of beta I minus f of alpha I, right. Well, this is the modulus because this is positive, right, this is greater than or equal to 0. So, I can put a modulus if I want. So, if I put together the statement that so m of a less than delta implies nu of a less than epsilon is same as saying, so this is equivalent to summation, well, at least it implies, let me not say equivalent to, this at least implies that beta I minus alpha I equal to 1 to n less than delta implies nu of a is simply this summation I equal to 1 to n. I will put a modulus just to make sure that this is exactly like what we have earlier, okay, minus f of alpha I is less than epsilon. Modulus is not necessary because it is greater than or equal to 0, right. But that is the definition of absolutely continuous function, right. So, f is an absolutely continuous function. So, this is the connection, okay. So, we will continue. So, absolute continuous functions and absolute continuous measures are sort of related to each other, right. So, let us start with the first result in this section. So, theorem small f from AB to RB continuous. So, that is an extra assumption we will put, and non decreasing, okay. Well, that is just the one step, okay. So, then the following are equivalent, So, first one, f is absolutely continuous on AB, okay. B, f maps sets of measure 0 to sets of measure 0, okay. C, f is differentiable almost everywhere, that means there is a exceptional set has measure 0, outside that f is differentiable. So, f prime makes sense because f is differentiable almost everywhere, derivative is defined almost everywhere, but the derivative is actually an L1 function on AB, and we have the fundamental theorem of calculus, and f of x minus f of a equal to, or f of x minus f of y if you like, f prime t dt, okay, for x in AB of course. So, these three are equivalent. So, this is the theorem. So, the second one should ring a bell because we constructed, remember we constructed a Cantor function which mapped the Cantor set to 0 1, closed interval 0 1. So, that did not map a set of measure 0 to set of measure 0. So, it cannot be absolutely continuous. In fact, its derivative is 0 almost everywhere. So, that the assertion here will not be even correct. So, that is an example you can keep in mind. So, let us prove this, but remember we have some assumptions that it is continuous and non decreasing, okay. So, small f is sort of increasing in some sense, okay. So, f prime should be positive, okay. So, we will prove this, and then we will remove the assumption that it is non increasing and things like that. So, it is very similar to what you have seen with measures in some sense. As you go through the proof you will see. So, let us start with the proof of A implies B. So, A says that f is absolutely continuous, then I want to say it maps measure 0 sets to measure 0 sets, okay. So, suppose you take a set E inside AB with the measure of E is 0, right, Lebesgue measure of E is 0, okay. We need to show that. So, what do we need to show? It maps sets of measure 0 to sets of measure 0. So, to show that f of E, so that is the image of E under f, right, f of E. To say it has measure 0, I have to say it is actually a Lebesgue set, right. So, first of all it has to be measurable and measure of this set is 0, right, that is what we want to show. Okay. So, we will assume that this is a very simple assumption. Assume that E is actually contained in the open interval AB instead of the closed interval. That means we are assuming the endpoints are not there. Endpoints anyway have sets measure, they are measure 0 sets and they will be mapped to 2 points, right, at the most, and so that will have measure 0. So, you can always add the endpoints later. So, this assumption is without loss of generality. Okay, we do not lose anything. Okay. So, assume that it is contained in open interval AB. So, you can choose epsilon positive, okay, and set delta positive from the definition of absolute continuity, right. So, if I take an epsilon positive, I have a delta positive such that whenever disjoint intervals add up to delta, corresponding images have epsilon as a bound. Okay. So, now since E has measure 0, by appropriate regularity theorems, there exists an open set, right, V. Well, what is the property of the open set? E is contained in V and of course, this is contained in AB, okay, such that measure of V is less than delta, right, because E has measure 0. So, I can cover it with open sets which have measure as small as I want, but V being an open set is a disjoint union of open intervals, right, because we are on the real line. So, this is true. I can write V as union, well, it may be finite, but it can also be infinite. Okay. So, keep that in mind, I equal to 1 to infinity disjoint, right. So, disjoint union of any open set in the real line is a countable disjoint union of intervals, right. So, that is some basic theorem from topology you must have learned. Okay. But measure of V, since this is disjoint, measure of V, what is measure of V? Because it is disjoint, this is sum I equal to 1 to infinity beta I minus alpha I, right. That is the length of each interval, and since it is disjoint, this adds up, that is countable additivity of the Lebesgue measure, and that is less than delta, right, because of this. Well, so whenever you have intervals adding up to delta length, we know by absolute continuity, okay, by absolute continuity of f, we get summation I equal to 1 to infinity f of beta I minus f of alpha I, right. Modulus is not necessary because f is non-increasing, right. So, is less than epsilon. So, recall that f is non-decreasing. So, non-decreasing. So, modulus of f of beta I minus f of alpha I is actually equal to f of beta I minus f of alpha I. Okay. So, there is a catch here because these are infinite sums, right. So, these are infinite sums. In our definition of absolute continuity, there is no infinite sum, right. These are finite. So, for any finite n, we have this sum to be less than epsilon. So, how do I justify this? Well, you can do this for any finite sum, right. So, justification for this. So, let me put this in bracket, justification. So, if I take I equal to 1 to k f of beta I minus f of alpha I, then I am looking at a finite sum and I am looking at the intervals alpha I beta I only up to I equal to 1 to k, right. but I equal to 1 to infinity, if I take, the measure is less than delta. So, this is a subset of that. So, this will also be less than delta, and so this is less than epsilon, right. And so, if I take the limit as k goes to infinity, I will still get this, right, less than or equal to, let us say, okay, just to be clear. Okay, so the absolute continuity immediately implies the same for infinite sum. Now, well, what is our aim? I started with a set which has measure 0, and I want to see what happens to the image, right. So, we started with a set E which was and we chose an open set O V, right, whose measure is less than delta. So, this implies that f E will be contained in f of V, right. But recall f is increasing or f is non-decreasing, which means if I look at the union of alpha I beta I, right, and f of that, well, this is sort of contained in f of beta, alpha I comma f of beta I, okay. So, let me write it properly, f of alpha I here, and take the union, right, okay. So, we get f of E is, right, because this is my V, right. So, f of V is sort of contained in this union because f is non-decreasing, okay. So, f of E is contained in this countably many intervals. So, f of alpha I, f of beta I, and you look at the closed interval I equal to 1 to infinity. So, measure of f of E, right, that is what we want to find out, is less than summation I equal to 1 to infinity, right, f of beta I minus f of alpha I, right, because each of these intervals have measure f beta I minus f alpha I, which I know is less than epsilon, right. For the infinite sum we just proved this. So, this is less than epsilon, and this is true for every epsilon, right. So, this implies that the measure of this is 0, right. So, well, so I shouldn't say measure of f of E, because we do not know f of E is measurable. So, let me put m star, okay. So, m star of f of E is less than epsilon for every epsilon, implies f of E has outer measure 0, okay. So, anything which outer measure 0 is of course a measurable set. So, this would be in the Lebesgue sigma algebra of R, and outer measure is its Lebesgue measure, right. So, f of E is 0. Okay, so that is the first assertion. If I have an absolutely continuous function, it maps sets of measure 0 to sets of measure 0. So, now comes the stronger implication. If I have a function which maps sets of measure 0 to sets of measure 0, then it is actually absolutely continuous, and it has I mean, in the sense it is differentiable, and you have an L1 derivative, and you have fundamental theorem of calculus. So, this is precisely Radon-Nikodym theorem in disguise, which you have already proved. So, we will use that. So, recall that f is non-decreasing, or in other words increasing, but at some point it may not be strictly increasing. So, you define, so you make it 1 1 and increasing by looking at x plus f of x, okay. So, this would be 1 1 and increasing, right, because the function x is 1 1 and increasing, okay. So, check that G maps sets of measure 0 to sets of measure 0, okay, because f does that, and adding x is only adding the length of the intervals, but that can be made very small, right, that is what we just saw. So, this is sort of trivial, but you have to, I mean, it's a simple computation, but you should check, okay. Now, if we take a set, so remember we need to prove that f is differentiable almost everywhere, f prime is in L1, and the fundamental theorem of calculus is true. So, if E is a subset of AB, okay, and E is in the Lebesgue set, then I can write E as E1 union E2, where E1 is an F sigma set. So, this is a property of Lebesgue sets which we have proved, and E2 is a measure 0 set, right. So, that is how they differ from Borel sets by a set of measure 0. But G is 1 1, G is 1 1, increasing, continuous, right, because F is continuous, this function is continuous, and I am adding two functions. So, it is 1 1 increasing and continuous. Okay. So, then then G of E will be, because it is 1 1 increasing and all that, it would be also be GE1 union GE2, okay. But E1 is F sigma meaning union of closed sets, right. So, let us write this as Fk, k equal to 1 to infinity, these are closed sets, Well, closed sets contained in the interval AB, right, because everything is contained in the interval AB. So, they are compact sets, so compact. So, GE1 will be union k equal to 1 to infinity G of Fk, but G is continuous. So, it maps compact sets to compact sets. So, these are all compact sets, right, and so they are also closed. So, this is a F sigma set because it is a countable union of set, okay. So, GE1 is F sigma set, and by the assumption on F, so F maps sets of measure 0 to sets of measure 0, adding X does not change that property. So, G maps sets of measure 0 to sets of measure 0, and E2 is a set which has measure 0. So, G of E2 has measure 0. So, what did we prove? GE is the union of an F sigma set and a set which has measure 0. So, GE will be a Lebesgue set. Okay. So, GE is measurable. So, whenever E is measurable, G is measurable. Okay. Right, that is what we just proved. So, if E is a Lebesgue set, then GE is also a Lebesgue set. So, we just proved that, and this allows us to define the following measure. So, that is where the Radon-Nikodym derivative comes in. Define a new measure mu of E to be equal to measure of GE, right, where E belongs to the Lebesgue sigma algebra of the interval AB, right, everything is happening in the interval AB. Then, okay, so then mu is a measure. Well, first of all, everything makes sense because GE is a Lebesgue set whenever E is a Lebesgue set. Okay, so there is no problem in defining. Mu is a measure. Why is that? Because G is 1 1 increasing. Okay, so if I take disjoint sets E1, E2, etc. disjoint, then GE1, GE2, etc. will be disjoint. Okay. So, if I look at mu of union Ej, where Ej are disjoint, then this is measure of G of union Ej, but because it is 1 1 disjoint, etc., this is measure of union GEj, right. All this 1 1ness, etc. are very crucially used at these places, but this is a disjoint collection because G is increasing, strictly increasing. So, disjoint sets will go to disjoint sets, and so this is the sum of M of GEj, because M is countable additive, which is same as mu of Ej by definition, and so mu is countably additive. So, that is why mu is a measure, right. So, that is easy, but that is why you are adding the function x to make it 1 1 and increasing, so that disjoint sets go to disjoint sets. Okay, so mu is a measure, Well, so let us recall the definition. Mu of E is equal to M of GE, but remember G takes sets of measure 0 to measure 0. So, now if I take E such that M of E is 0, then M of G of E, so G E has measure 0 because G takes measure 0 sets to measure 0. So, this will be 0, which is same as mu of E is 0, right. So, whenever M is 0, mu is 0. So, what do we have? We have absolute continuity. Hence mu is absolutely continuous with respect to M, and mu is bounded. Mu is a finite measure, okay, finite measure, right, because everything is happening in a compact interval. Okay, so this tells me that it's a positive, well actually it's a positive finite measure. So I have a sigma finite measure M, which is actually finite, and I have another finite positive measure mu, which is absolutely continuous with respect to M. So by the Radon-Nikodym theorem, there exists H, the derivative, right, the Radon-Nikodym derivative in L1 such that d mu is equal to H dm. Okay. So all that we have to do is to write it up. So G of the interval Ax, well, what would be this? This, because G is 1 1 and increasing, this is simply Ga Gx, which I know is the length of the interval, which is Gx minus Ga. But what is this? Okay. So that is G of that set, correct. So the measure of okay, so I should say measure of M of this equal to M of this equal to Gx minus C, but this is mu of the set Ax, right. Mu of E is M of G, okay. So this I know is Gx minus Ga, right. So let us write this in a clear form. So remember, mu is absolutely continuous with respect to the Lebesgue measure. So I have H dm there. So this implies integral a to x. So I am writing it in this form, H t dt, correct, right. So this is simply the mu of Ax, because mu is h d mu h dm, and that is Gx minus Ga. Okay. So that is essentially the fundamental theorem of calculus, but G is not the function we want, right. So Gx minus Ga is x minus a plus fx minus fa, right. Okay. So for this we know the fundamental theorem of calculus. So we simply put that in and bring it to this side. So bring it to the left hand side, we will get fx minus fa is equal to integral a to x h t minus 1 dt. Okay. So we have proved that f is differentiable and f prime is equal to h t minus 1, and the fundamental theorem of calculus is 2. Okay, so I'll stop with this. So the last implication I leave it as an exercise. Use Lebesgue differentiation theorem. Okay, Lebesgue differentiation theorem. Okay, so let us stop here. So we just took the first step in looking at absolutely continuous functions. Okay, so in combination with the Lebesgue differentiation theorem, we just proved that if I have an absolutely continuous function, then it maps measure 0 sets to measure 0 sets, and any such function is absolutely continuous, and you have the fundamental theorem of calculus. Now in the next session we will, so recall that we assume that f is non-decreasing, so f is sort of increasing. So we will remove that assumption, we will simply look at any arbitrary absolutely continuous function. Okay. So for that we define what is known as the total variation function. That is what we used in the complex measures, right. So it's a very similar argument. Okay. So let us stop here.